All right.
All right.
Okay, so these are not the major topics that need a full 2 hours of lecture. These are smaller topics, so that's why there's 4 in one session. But these are equally important in that they each of these mini lectures covers one area of technology or one set of techniques for programming that are highly valuable. Otherwise, they wouldn't be here at all in the first place. So we're starting with pulse width modulation. Just to let you know, I'll probably do 2 of the mini lectures, then we'll have the break, and then we'll do the other 2. That's the plan. But if you know, it may adjust slightly. So pulse width modulation is a pattern of a pulse on a pin of a microcontroller that we can use to control devices, especially servos. So although this has other uses as well, it's mainly of interest because of controlling servos, certainly from a course like this perspective.
Richard, could you share your screen?
I thought I already had. Oh, sorry, I thought I had. Sorry. Luckily, I'm still on the first slide, so I haven't actually changed slides yet. Is that not showing now?
No.
Does this not show as shared?
No.
Ah.
Yeah.
How about now?
Yeah.
Right. Okay. It doesn't matter because I haven't changed slides yet, so you haven't missed any slides. Move on to the next slide anyway. So when we talk about pulse width modulation, we're talking about a voltage pulse, a pulse of signal on a pin coming out from the microcontroller, which we can connect to various things. But as I said a moment ago, mostly we're concerned with servo control, because the way a servo works is the width of the pulse governs the position. The servo basically turns to a certain point in different positions, and that's controlled directly by the pulse width. So first of all, we need to make sure we know what we mean by pulse width modulation. So imagine we have the voltage is 0 or 5. We can draw some, all of these waves, by the way, are in some regards called square waves, because they are basically just form a square shape. But a true square wave has a 50% duty cycle, which means it's 50% off and then 50% on in terms of time. So it's off for, say, half a second, on for half a second, off and on like that. That would be a 50% duty cycle, and that is what is correctly a square wave. But these other waves are also sometimes described as a square wave as well, because they have the same basic characteristic. They just don't have the symmetry. Okay, so obviously, if you look at the amount of energy that is delivered to something, there's more energy in this pulse. This is on most of the time and just off for a short time, and this is off for most of the time and just on for a short time. So we could use this as a means of controlling the amount of energy delivered to something, and we talk about that with LEDs in particular later in the lecture. And we also could use it as the length of the pulse meaning something in terms of a control sense, and that's how we use it with servo. So we can use this in at least 2 interesting ways. So the next thing to realize is how, so we now know what the pulse width modulation signal looks like. How do we generate this signal? How do we create this signal on the output pin of the microcontroller? So on the microcontroller, we have several pins which are labeled output compare and then some numbering like this. So if I now switch to the PDF manual for the chip, this favorite manual that you've seen many times, if I put this here and enlarge it, now this is the pin connection of the microcontroller, And the bit I want to show you is really this bit here, because it's probably the most interesting part of where there's three of these output compare pins close together, but there's many other ones on the chip. There's another one there, look. But these three, output compare 3A, 3B, and 3C, these three pins here are particularly interesting because these are all connected to timer 3, right? And this is showing you that timer 3 can produce 3 of these wave patterns. That's just one timer. So you've got 6 timers altogether. Some of the timers can produce 3 wave patterns. Some of them can produce 2 wave patterns. So in total, you can produce more than 12 different servo control signals or pulse width modulation signals from the one microcontroller, which is more than most robots need. Most robots have 6 or so axes maximum. So you could make a robot with 6 servos controlled directly from the microcontroller without any shortage of pins. But the important thing here to realize is one timer can actually have more than one of these output compare signals, and also to realize that the output compare signal is just on a pin like any other signal on the microcontroller. There's nothing particularly special about this pin. Obviously, it can be just a normal output like a digital. This would be part of port E. So we could use this just for normal, 1-0 type input or output for port E. But we could also use it as other things. We looked at the analog the analog comparison before. That's one of the uses of this pin. But this is another use of this pin. So do you remember we looked at that table of alternate functions for the port pins? These output compare functions are the alternate functions of several different pins on the chip. And as I say, there are many spread around the chip, but these three, because they're all clustered together and they're all on port 3, these are a nice example to focus on. Now let's go back. Let me bring that out of the way. I'll keep it open. Let's go back to this slide. Now here we have some labeling which is generic. So OCN means it could be any of the output compare pins. We don't need to know which one for this diagram, okay? But obviously you would have to use output compare 3A or 0, whatever, because you can use these on any timer. It depends on what timer you've chosen and whether you're A and B. Now, some of the microcontrollers, not the one you use, but some of the other Atmels have an alternative upside down version, inverted is the proper word, version of this signal on a separate pin. So whereas the signal might look like this, that's the actual output compare signal, some microcontrollers automatically allow you to have the inversion of that as well, which can be useful in many things. Okay, but in this particular microcontroller, we don't have that option. But I leave it on there because it's something, if you're working as an engineer, you will come across this in some chips. And also, just because we're using the 2560 on this course, you mustn't think that this is the one you will definitely use in a workplace or in further study or whatever else you do, because this is a good example, but it's not the only one out there. So this is an important concept in some control circuits, that you have the signal and the inverse of it, the inversion of it. Okay. Now, this line here is the most important on the slide. Okay, this is the timer, and this is the timer counting, right? So if you imagine time is running this way, which it always does, and this is the count value, it doesn't go from 0 to 1, does it? It goes from 0 to, let's say it's an 8-bit timer. Then, so use timer counter 0. Then this will go from 0 to 255. And if you add 1, you've only got 8 bits. It will go back to 0 again, because 256 and 0 are the same thing if you've only got 8 bits. So this would go 0, 255 eventually, 0 again, 255, 0, and it keeps doing it. But that is what we call a sawtooth wave, and that is obviously not a square wave, and that's a kind of it's a form of triangle wave. We call that particular one is called a sawtooth, and obviously that's not what we want. But if we use the position at which it goes back to 0 as a sort of marker, we could say, well, that's the beginning of something, and this is the episode, and then it starts again. So some kind of cycle is going on here, right? Okay. And if we then say, well, what if we set a midway marker, and that's the other part of the cycle? Well, the midway marker is the is basically when the count value matches what we call the output compare value, which we already talked about when we talked about timers. This is how you set the time interval. You set a value which is called the output compare value, and you set that value to be where you want to count to. So basically the counter starts at 0 and it starts counting up, and when it gets to the value you've chosen, that causes, in the previous examples, that caused an interrupt. Here we don't need the interrupt, we just need to know it's matched that value. So we have 2 points now. We have the point where it starts the count, or where it ends the count, depending on your viewpoint, it's the same place. And the point where we reach this, well, I call it a halfway mark. It's obviously not halfway, but it's in the middle somewhere, right? This middle position that we choose. And if we then look at the ratio of this bit against that bit, so if we, supposing we set it halfway, we would, like, this is nearly halfway, isn't it, here? So this would give us the square wave output we were talking about before, because if you start off high for halfway and then you make it low for the other half, so if we set this at 127, so 0 up to 127, that causes it to change here, and then the other 127 or 128, yeah, it's nearly half, yeah, goes up, and so you get this square wave. So that would be with the output compare halfway up the counting range. Obviously, if we set the output compare near the bottom of the range, supposing we go 0 up to say 20, and then carry on to 256, you'd have it's only on, the pulse is only on for a short time and then mostly off. But if we set the count to be, say, 200 maybe, then you can imagine it would be on most of the time and then just off for a shorter time. Okay, so by setting the timer count values, we can control the shape of the pulse. That's the important part from this slide. You don't need to memorize every single part of this slide to understand the important point, right? We are changing the timer timing values in the registers, and by doing that, the pulse on the pin is changing. That's what you must understand. And the pulse on the pin is a square wave. It may not be a pure square wave, 50%. That bit there is approximating that, but the rest of it isn't. And we can change this. The other thing to notice, obviously, is we can change this whenever we want. So we don't have to fix it like this. Our program can adjust it as we go along. And that's important, because if you imagine a robot, it doesn't just move to one place with the servo turning and it goes to there. Maybe the servo, the arm is moving. Maybe you've got several bits of the arm. That goes there, and then that one comes here, and so on. So these servos are moving all the time. They don't just go to one place and stop. So you wouldn't want to have this fixed, because it wouldn't really work with a dynamic application. So we can program this to be anything. And we can even change where the top is, but that's more complicated and we don't tend to bother with that. But the flexibility is there. Normally, the top is just where the overflow interrupt would normally occur. And we can have an interrupt as well if we want some software action as well, but we don't need them here. It's a hardware action. This translates directly into a pulse. We don't need any interrupts going on at these points, but this is where the interrupt would occur. This would be the overflow interrupt, and this would be the output compare interrupt. Okay, so it's really the ratio of timing values here maps onto the ratio of the high-low duty cycle. The duty cycle is basically what fraction of the time is the signal high. So if it's high half the time, then it's a 50% duty cycle. If we look at this part here, if it's high maybe 1 I don't know, 1/6 of the time, so let's say 1/5 because it's easier maths, right? If it's high 1/5 of the time, then it's a 20% duty cycle. All right, and that's really what we need to know on this slide. And these timing intervals, the actual periods, are always the same because this is going from 0 to 255 every time.
Can I just
All right.
add something, Richard?
Say again?
Can I just add something?
Yep.
Yeah. So if you look at the first sort of square wave pattern, that's the third period, right? I just want to clarify that in the first two periods there has not been set any point, and that doesn't mean that you can basically use those first two periods and count them so that you have three periods and then the value for that. So they're in isolation. You only have each PWM signal is calculated per period, because it might look like from this image that the first high or sorry, first low is actually after 2.5 to 2.75 periods, but it's actually not the case, right? It's not 2.75 periods. It's the first two periods you're not doing anything.
Yeah, there's two reasons that could occur, by the way. One is that the actual output the actual timer mode. When we program the timer, you will hopefully remember from the 5th or 6th lecture, when we program the timer, we set the mode of it, and it might not be in PWM mode. It might be being used for something else. That's one possibility. And the other possibility, although it's hard to show on a diagram like this, is that the output compare value was set to 0. So it basically went, so the pulse was essentially, in fact, no, it would have to be 255. If we set the output, if we set this right to the very top, we would essentially get this anyway, because it would kind of go down and up instantly at this point. So you'd essentially have the same look, not quite. You'd have a very minuscule, quick down and up there. But it would be just a matter of hardware switching. It wouldn't be a matter of any particular time interval. So yeah, I wouldn't worry too much about this part. The slide is only useful to us to look at this part here for now. There's a lot more, as with all of these things. If you read the manual in detail, there's always more levels you can go to with this stuff. I'm not expecting you to, on this course, to go into that real depth, that engineering depth, but there's loads more levels you can get down to with all of this technology. You need to understand here the relationship between programming the timer to set the different counting ratio, and then the effect of having this pulse here generated, and how that affects timers, servos or LEDs or something that's connected. So let's now move on to the next slide, which is actually connecting that to some LEDs. Now, the photos are blurred because these were taken in very low light quite a few years ago, and I didn't have a tripod handy at the time I was preparing this lecture, so I handheld them. The blur does not matter. What matters is the difference in intensity. This is like this is on the board I use, the control board I use. This is a power LED, so it's always on all the time, 100%. These are low intensity LEDs anyway. These are not particularly bright LEDs. These are normal, just like power indicator LEDs, so they're not very bright. But here you see, this is in like a darkened room, so I could see the low level. You can imagine to the naked eye, you can barely see these are on. These are just barely glowing. This is with 0.5% duty cycles, which means it's on 1 part and then off for 200 parts. Okay, and this is 2%, which means it's on for 1 part and off for 50 parts. This is 12.5, which is approximately, well, is exactly 1/8. This is 1/4. This is 3/8. Now this is interesting, okay, because this looks like they're the same brightness, and it shows you that the actual brightness in a physics sense is different to the way an LED works and the way that I work and so on are non-linear, right? Which means that it may appear to be as bright as 100%, but it isn't. It's slightly less, but it's not linear, because you see, going from a quarter, so it's 2/8 to 3/8, it fools us into thinking this is on all the time. But actually, if you went higher and higher, these get slightly brighter, but they don't double their brightness or anything, because they can't, because, you know, as we see it, that is, to our way of viewing it. This is useful because you can actually use this for generating effects other than just purely LEDs on or off. You can have different brightnesses. And if you have a red, green and blue LED, by changing the brightness of each one, you can make multicolor LEDs, which is exactly what you can do with multicolor LEDs. But also, you can save power. If you have a battery operated device and you connect a LED, normally you only control the LED brightness by the value of the resistor you choose. But here we can control the brightness, and we can make the LED dimmer. For example, in daylight, we can use dimmer LEDs, and we can therefore save energy. So this is connected to green computing and prolonging the battery life in devices and things like this. So all these things are quite valuable in their own right. But this is actually only here as primarily my purpose of putting this here is not to do green computing with you. This is, although it's a useful thing to do, this is actually here to demonstrate the actual effects of the different pulse widths. All right, and there's a sample program you can actually look at, and you can run it. This one just conveniently uses the LED on the board that you've got, this demo program, so you can actually control the brightness of that LED on that board, and the code is there for you, just so you have a working example of this. But as I said at the beginning, really the real value of this is controlling servos, right? So there's always more you can do, right? So we say, okay, the real value servos. Well, let me just go back to that point. Okay, so here we can control, the brightness of LEDs. You could control other things in a similar way. You can control the speed of an electric motor in a similar way to this, like a power drill or something like that. That's got a speed control on it, because it's the amount of energy getting through that actually controls in the motor the speed of some motors, of course, not all types. All right, so really, once you understand what you're getting from this signal control, once you understand that, then it's a matter of your imagination and your knowledge of sensors and devices as to what you can do with it. And you can do more normally than I can just tell you about in a lecture. It's, you know, the more experience you have, you start thinking, oh, I could do something. This is interesting. I've got an option of this or that. I've only told you two there: motor speed, LED brightness. There may be others. But this is, as I say, coming back to this is what this is really about, right? Servos. A servo is a device that we can rotate, but we can precisely control where it goes to. So a perfect example to explain this would be a CCTV camera that we want to be able to rotate, but we want to be able to point it in a certain place. And we want to maybe have a controller in a watch station who can move a lever like a joystick in a game, and the camera will follow where he points the control stick, right? So maybe security control. So if you imagine that scenario, that's a perfect good example. And the robots, simple robots, is the other really nice, easy example to think of. Then we obviously, somewhere has to be some movement, right? We've got to have some movement. So a motor is needed, because how can you turn something, right? You need a motor. We need a gearbox, because we're not here considering turning something quickly. We're more concerned with turning something slowly but accurately, very, very accurately, actually. In fact, the accuracy is really the important thing here. So we need a gearbox so we can slow down the motor but also increase the power output. So if you have a small motor turning quickly, maybe can go quick, but it doesn't have much power, much force, much torque. Being the proper word for it is torque. Rotational energy, rotational power is torque. But if you have a gearbox and you rotate, you slow your rotation down by 1,000 to 1 or 5,000 to 1, these are typical values inside these servos, then your torque goes up by that much. So you end up with a very slow moving device that's very, very powerful rotation, but very slow. And this is what a servo tends to be. We also need to know where we're pointing. Where is the servo pointing? It's a kind of feedback system. If we turn the camera, we need to know when the camera reaches a certain place to stop turning it. So we need what's called a positional feedback system. And that is, I'll show you in a minute how we do it. There's several different ways we can make that work, and a control circuit. And that's obviously so that when we reach the feedback position, the servo stops moving. So we talked about the gearbox. The positional feedback is provided by a thing called a shaft encoder. There's multiple ways to do that. So a shaft encoder is something that if you have a rotational shaft, so the axis that can rotate, how do we know how far it's rotated? We need something attached to it that we can detect. And a nice easy way to do it is to have an optical one, which is like a disc. Imagine a disc with all holes cut in it. So imagine a disc with these slots cut in, and light can shine through these slots. And as we turn the servo, the disc also turns, right? So imagine it turns with the shaft, and the light goes through, and we can count interrupts. If the light beam is interrupted, we can connect that to a sensor. We can say, okay, the disc has turned a certain amount because we counted these pulses of light going through and it being interrupted. And so an optical one is commonly used. We also have magnetic shaft encoders, where you basically detect a series of magnetic pulses. If you imagine now you have like a cog, and you have a magnetic detector here, basically as the cog rotates, so anything ferrous metal going past, you detect pulses as they go past the sensor. Okay, you have a magnetic sensor here. Okay, and as the wheel goes past, you detect, and you know how far it's been turned. Okay, and another simple way to do it, probably the most common way for servos, is to put a variable resistor in the gear train, which, so you know how variable resistor works. You turn the dial and the resistance changes as you rotate the dial. So why not connect that to the cogs, so that as the cogs turn, the variable resistor rotates, and that gives you a different resistance. And that's the simplest way to do it. And that is the way that most cheap servos work. So if you're buying a cheap servo for maybe anything less than 200 krona, for example, then it's probably done like that. If you're putting a really expensive servo in a really big industrial robot, it probably will be an optical shaft encoder. But some of those servos are, many thousands of krona, and they are a different level of precision to the ones that you have, in small devices, in cameras. The zoom on a camera, what makes the lens come in and out and zooming and stopping the lens at certain positions, that is a servo. But it's got, obviously there's a linear movement coming from that. So maybe a certain set of gears and a worm drive of some kind to drive the lens out. But inside the camera, the servo will turn, and that will maybe be connected to the lens. So as the servo rotates, the lens is pushed in and out. So what controls your in-out zoom will be a servo inside your camera. So these can be quite small as well, these servos. Okay, so obviously the control circuit needs to understand the way the feedback is coming back from the positional shaft encoder, and the signal you're sending to the servo, which is your pulse width signal, saying what value you want the servo to go to. You compare the two and you see if you have to turn left, right, or if you're in the right place already. We've already talked about the application, so I won't dwell on that slide. We've spent quite a lot of time talking about that. here is a sort of schematic diagram. You have the motor, which turns this, but you don't want it to turn quickly. You want it to turn slowly, but with more torque. So we have a gearbox to convert a fast motor that's got low torque to a slow output shaft with high torque. And this is a shaft encoder. We don't really care in this diagram what type it is. This is more like the way an optical one would work. So that's why I've called it an optical one here. But the diagram would be similar if it was a magnetic one, right? So this rotates with this, and somehow we detect the rotation. In this case, a light beam, this would have slots in it. And as it goes through, breaks the light beam, we know how far it has turned. But it also can be magnetic. There are other ways of doing it. We don't need to worry too much for this side. The important point is that we do somehow know this is rotated. We get a signal coming back, and we have the signal that we're sending from the pulse width from the microcontroller here, which will obviously, continues, but it's just a small part of it. And you actually need to compare what your, the position you want with the position you've got at the moment. And that determines which way to turn the servo. Because if you're turning the camera might go beyond where you tell it to, and it's going to come back. It may go slightly back, because you maybe you move the control stick too quickly or something like this, or maybe the wind blows the camera and the servo realizes it's gone too far and it comes back, because the servo will adjust itself all the time because of this loop. So that's another thing that's quite interesting about servos. If you were to grab this and pull it round, so suppose you've got a camera that's pointing a certain way, and you actually physically grab the camera and pull it, the servo will know it has moved because of this, and it will actually pull it back. So if you grab the camera and turn it, it will go back. The servo will actually sense that it's not pointing in the right place and will pull back. So there is intelligence in here as well, as in your microcontrollers here sending this signal, but there's another microcontroller in here doing this positioning. Okay. This is the range of pulse widths. Okay, so the interval, and let me just come back to that very first slide we talked about here. This interval here, right, between these, the whole cycle of going from 0 to 255, that is the same interval that we mean here, from there to there. And that is typically 18 milliseconds. Servos are designed, there's a kind of industry standard. Every one I've used in the last, I don't know how many years, but it's definitely more than 20. Every single one of them has conformed to a range of between about 16 milliseconds to about 19 or 20 milliseconds, and 18. In fact, I think the actual recommended standard is something like 18.2 milliseconds or something, right? But as long as it's between about 16 and 20, it works. And I've tried it with quite a few different servos. So we always aim at 18, and all my sample code aims at 18 and near enough 18, because it's in a safe range. Okay, and the servo electronics in that control circuit are expecting a pulse to be in that kind of range, and then it will look for the edge again. If it sees the edge between after 16 or up to 20, it will know it's a new start. If it sees another pulse somewhere like here that it's not expecting, it will get confused, and your servo might start doing weird stuff. And it's definitely no control system I've ever come across would like that weird stuff happening. You avoid that kind of thing. So your pulse needs to be set to be repeating every 18 milliseconds. Now, within that, the actual width of the pulse has to be controlled to give you the meaning that you want, to translate into a position. So there's a range of values that are valid. You can't use this whole range because for safety reasons, it has to have time to respond to that before the next one comes. Because remember, a servo is an electromagnetic device. It moves, and it's got this gearbox, which makes it even slower. It's very slow. This, you can't expect to send a pulse that would maybe end here and then the servo to get there, and then the next pulse. So the idea is that this, by having only a short range of pulses here in the whole range of possible pulse widths, you actually allow the servo to adjust before the next pulse comes in, right? And if you imagine the servo position is linked to the pulse width, so the pulse width that is actually useful to us to control the servo, it has to be normally at least 500 microseconds. This is the shortest. So that's half a millisecond, right? And then the maximum is 2.5 milliseconds, or 2,500 microseconds. So the duty cycles are all quite short. They're all, this is 18 milliseconds. So if this were 20 milliseconds, just to make the maths a bit simpler, and that was 2,000 microseconds, that's 2 milliseconds. That would be a tenth of the whole thing, right? So the duty cycles are all quite short, in the region of 1, 2, maybe up to 10%. So they're all at the short end of the range, but it doesn't matter as long as you follow the timing rule. So between half, so you've got to have at least some signal, half a millisecond up to 2.5 milliseconds. So this is the range of variation. Okay, so if you have this length pulse, it would be at the far now it depends which way you look at it, whether you look at it from above or below, whether you call that clockwise or anti-clockwise. And sometimes in designs, this is where engineers can get confused. Someone draws a diagram looking from the top, someone else interprets that diagram looking from the bottom, and the servo goes the wrong way in the final product, things like that. So coming back to your coursework, this emphasizes, not just for servos, but for anything, how important it is your documentation is clear. Because this is an example where I've personally made mistakes and confused myself, and I've designed it perfectly, and then the servo in the product, the servo goes the wrong way, and you have to rebuild certain bits of your code. It can be quite annoying. Obviously, that's where testing comes in as well. But so if I say to you, this is moving from there through to there, and I call that a clockwise movement, then you've got to be careful in when you interpret this. Is that looking up the shaft or down the shaft of the servo? Things like that you may take for granted, but the engineer who's got to build this may get very confused. So there's always these terminologies. But anyway, if we call this maximum anti-clockwise, then we can say that is the central position, and that is maximum clockwise. And the other thing to say here very quickly is that typically for a servo, you only get 180 degrees movement, or maybe 190 degrees on some of them. You don't get full circle rotation in most of these servos. Okay, I'll move on. This is what one looks like. This is a typical miniature servo, and in your kit, there normally is an even smaller than this servo in the previous kit. Stephen, is that correct?
Yeah, we have.
You do have one.
A small blue servo.
Yeah. You have this is about 4 times as big as the one in your kit. This particular one. This is good for small robots. The one in your kit is a bit too small for robots, but the one in your kit is good for like model aircraft or model boats and things like that, where they use them to control the wing flaps and so on. And you need a really small, light little servo. Whereas this one here that I use, myself. These are brilliant servos, but these are better for, say, a camera control, something like that. They're quite heavy duty. These are quite cheap and quite heavy duty. And I actually love building things with servos. It's a lot of fun to see things start moving and so on. Anyway, it doesn't matter. They're all they work basically the same inside. But this particular sort of size, which if you look up this one later, if you look up the high-tech number, it's on there, 475 HB. The HB, by the way, and these numbers actually mean something. The HB are to do with the gearing, and whether it's got brass gears, plastic gears inside, things like that, whether it's got a certain gearbox. So you get the same thing with different gearboxes. So they move faster with more or less torque and things like that. So these numbers mean something. But basically they all work the same. They've all got 3 wires, and the wires will be a 5 volt and a 0 volt, so ground, and a yellow or sometimes white wire, which is your control pulse. So the yellow is also white in some servos, but this is a normal. I've never seen anything else other than black, red, and yellow, or black, red, and white. All right, but there may be other colors. I've never seen them, but it doesn't matter. And
Richard,
yep,
could it be that that we're missing one statistic that says something about how fast it goes per?
yeah, this particular one, I haven't put it on here, but if you look at servos on the internet, you'll see that quite quickly. It tells you how many degrees per second or per millisecond it can rotate. Okay, this particular one, just to give you a clue, takes about half a second to rotate fully from one end to the other. Okay, it's about half a second. It's not a very fast servo, but it's very precise. And these are really cheap and really quite robust. I really like them. This is just one example. There's so many types out there. So I don't want to go too long on one particular servo. I'm just giving you an example that I know very well, so you can imagine trying to build things with these servos, what it's like to actually build things with these things. The torque, 3.4 kilograms per centimeter. This is really amazing. So if you had a lever 1 centimeter from the center, which this is actually probably 2 centimeters anyway. So if you attach a piece of string to a hole, this has got little holes in it so you can attach the equipment. If you imagine attaching a piece of string to a hole 1 centimeter from the center, say about here, and you have that vertically hanging down. So your servo is like, there's your disc, and you have the string attached to it, and you want to raise that piece of string by rotating your servo, then if you attach 3.4 kilograms, 1 centimeter from there, this would raise that. That's a lot. That's 7 pounds in English, old weighing technique. 3.4 kilograms on this little thing. So you can imagine quite a heavy arm of a robot could be moved with this. Okay. This is what they look like inside. This is the little controller, which is itself a microcontroller that controls the position. This is the bottom of the motor itself. These are the power connections. The motor is mounted here. Okay. And these are power transistors here, which control the direction of the motor. All right. In the top, so now that view you just saw was looking in the bottom of the servo. You can take these things apart. The top and bottom comes off. If you do take them apart, be careful, because you'll never get the gears back in. Once you take this apart, you'll have a load of cogs on the table. Be very careful. Getting them back together is not at all easy. But this is one taken apart to allow you to see it. You have all these gears, and this is the connection of the shaft encoder, which is a variable resistor, and this is connected to the gears, and it's connected on the output side. So this moves slowly, so does the shaft, rather than on the motor side, which spins quicker. I won't go through all the gear train with you, but by having multiple cogs in a gear train, so it's quite a compact gearbox. This has got plastic gears, this particular one. You actually get about 1,000 to 1 ratio between this spinning around 1,000 times a second and this may be rotating once per second or something like that. Okay, so now if we look at the pulse width on an oscilloscope, and we actually so where I got this diagram, this is done in one photograph. This is not stuck on separate. This is a piece of paper resting in front of the oscilloscope controls, so you could see both at once. You can actually see, if you zoom in, it's actually got a serrated edge of paper there, and you can see the bottom with a bit of paper there. And so this is literally a live image, because this was done a few years back, because I wanted to actually show people directly. This is the pulse width. This is the 1500 is the middle of the range, and that's called the neutral position or the central position. Okay, the proper name for it in servo language is neutral, right? But you can think of it as central as well. And if that's 1500, and then this is so this is 1500 microseconds, and this is 18 milliseconds. That's basically 1.5 milliseconds, and that's 18 milliseconds, and that is the beginning of the next pulse. All right, I've set the oscilloscope to show just exactly one pulse, but because of the limits of my old oscilloscope, I can't not have that. But it's useful to have that because that shows me that's basically that bit being repeated there. And this is just it's not the most expensive oscilloscope in the world, and there's a limit to what I can do with it, but that's perfectly a good example. There's your pulse and there's your off time, and that's the equivalent position. So I've lined it up with a big red line on it because this white disc with the holes in it hasn't normally got any lines on it, and you can't see where is where. All right. These are because you can control, you add little rods onto this or connect or screw things onto it so that you can turn things. That's what that's for. Right, so this is the sequence of photos taken with different pulse widths. So this is the 750 microsecond, and you see the servo rotates to there, and then the 1500, and then the 2250, it will rotate to there. So you change the width of this, and this rotates to different places. And you control the width of this by changing the timer values in your program. Okay. Here's a simple example, which I'm going to whiz through very quick. You can look at the code later. I'm just going to whiz through. This is an example where I set, if you just go back to that slide there, imagine pre-selecting 8 positions where this can go to, right? So suppose you've got, here's a simple example. Suppose you've got a camera, CCTV camera, and you've only got one camera, and you've got 8 places you want to look at. Maybe like in a big part of an airport, you've got a big room full of people with all their luggage standing around, and you want to scan this whole room. And you maybe want to say, okay, have a look there, then turn a little bit, have a look there, turn a little bit, look there, and do this automatically. Rather than a sweep, maybe you just want to look steady. Maybe the face recognition software works better if it's steady. So you go, okay, look there, then turn it around slightly, look there, then look there. And you can imagine this one camera is rotating in 8 places and then coming back. So you might want to say, well, let's preset 8 increments, right? And we'll have 8 different pulse widths that correspond to those 8 positions. And we can make a program where the camera points over there, then there, then there, then there, then there, and then goes back to there like that. Okay, and that's automatic. And that works better than just going like this. Because if you move a camera like this, sometimes the image is just blurred and it's not really good for a security point of view at all. So maybe this is better. Okay, so I'm just giving you a scenario where you can understand why this code is useful, but it's really only there to demonstrate how servos work. So, maybe you don't need 8 places, whatever. But anyway, connects 8 switches to one port, right? And so each switch would have a different bit value, 0 to 7. And then you need a series of patterns. This is just defining these values. So each of these codes corresponds to one switch being pressed. And then we can, when we do push a switch, this is actually not automating the camera movement. This is saying the user can push whichever switch the user pushes, the camera will go to that place. All right, so it'll automatically go to whichever position is connected to that, is logically connected to that switch. And then we basically, this is just code to read the switches and decide based on the switches to set the position of the camera. Remember, we're talking about the minimum pulse, the pulse width in microseconds. In this particular program, I've used a 16-bit timer, and I've configured the timer such that a count of 1 on here is equivalent to 1 microsecond. Okay, you'll see I'm not going to go through every line of code in that detail because you can read it later, but that's what I've done. So by setting this value in the timer register, the timer will point, the servo will point to the minimum pulse width. So switch 0 takes it to one end, right? And then by adding on these increments, don't worry about the maths right now. Basically, this is me just dividing between 750 and 250 in this range. I've divided the difference by 8 increments, and this is me just adding on one of those eight increments each time. And in fact, this is where I'm adding on, if that's 0, and then add 7 increments on altogether, because you've got 0 plus 7 more. So this is where I've added all 7 on, yeah? But you can imagine the ones in between, it's this plus that times 1, this plus that times 2, and that makes up this interval. So each time you push a different switch, it would go around in 8 equal stages altogether. Okay, that's just simple control. There's nothing about servos in here really. It's just simply switches and setting a value in a register. But that's the important bit, because that's how the user would control it. All right. But this is the register value that controls where the servo would point. It's this number, that plus, if you add that up, and if you add that up, you get to almost exactly that. All right, because obviously we can't do fractions. So this is the closest I get, but that's pretty good. It divides it pretty accurately. All right. Okay. Standard setting the ports. Because port E is generating pulse width modulation, it does need to be set to output. That is one requirement. Although the PWM is an alternate function, you still need to set the port E to be an output for that PWM to actually appear on the pin. That's a good mistake for beginners to forget to do that, and then nothing seems to be happening. Okay, so you obviously have to think about the whole chip and what you're doing. We need interrupts for the timer. No, we don't. Sorry, we don't need the interrupts for the timer. We need interrupts for potentially for the switches. Not necessarily for the timer in this case, actually. Depends how we're using the switches. Right, so the timer, again, I'm not going to go through all of this code because you've got the timer examples, but we didn't have a PWM example in those timers. So I will just go through the differences here. And really, simply put, the only real difference here is setting the mode, right? So the waveform generator bits, which are the bit 0 and 1 here, and also bits 4 and 3 here on timer 3. These 4 bits altogether have to give us the mode for PWM, and there's different PWM modes actually. If you go back and look at the timer in the manual, and I'm using a mode called fast PWM, and in fact the full name of it is fast PWM ICR3 top, right? Look at the manual to see why that is at. You don't need to know exactly why there's different modes PWM, but if you use this value 1101 there, that will give you a nice, easy to use PWM generation. So that would mean you've got to put in bit 0 and 1, you've got to put this 0, 1 here, because this is 0, 1, 2, 3. And in bits 2 and 3 here, you've got to put these values, these 2 bits, right? So 0, 1, 2, 3, okay, of this signal. So this is bits 0 and 1, so they would have that part. And this is the bits 2 and 3, and they would go in here. All right. So when you look at this pattern here, you see we're not using these other modes anyway. So these 2 bits here come from that. And bits 3 and 4 here, so 0, 1, 2, 3, 4, these 2 bits have that part, all right? And then we're using the prescaler of 1, that's the prescaler, but same as before, because I'm using a 1 microsecond clock on my chip. I'm using a 1 megahertz speed, and I want this to be clocking at one timer clock per microsecond, because that allows me that very fine control of the position. So I want this to be working at the fastest speed the timer can work at. So that's why I've got 001 there for the prescaler. So the rest of it is pretty much the same as the timer lecture. We've got I'm setting the high not to be the overflow. Remember I said earlier we can set the high point to be anywhere. It doesn't have to be an overflow level. So I'm setting the high point where it starts again at 18,000, because that is my 18 milliseconds. That's so this pattern repeats every 18 milliseconds, and that's how I'm controlling that. And actually I can put the decimal in here directly if I want. I don't have to put it in hex, but I choose to, because I think if you're going to work in hex, you should work in hex everywhere. And I then go and contradict myself because I put the decimal value in there. So, but this is going to be fixed throughout the whole code. This is going to change as I reprogram it dynamically when the switches are pushed. This is the one that's going to be changing. This 18,000, which I've put as hex there, is going to control the interval between regenerating the new pulse. That's always going to be 18 milliseconds all the time. And then the actual timer itself will start at 0 and go up to 1800, and then we'll come back to 0 again, because that's what this register controls. And this is why we have this top. This is the top. Instead of setting the top to be the maximum of the timer, the top is the ICR register. And that's what that when I went back, when I said there, I'm using fast PWM ICR3 is top. That is saying don't have the top to be where the overflow is, have the top to be a programmable value, which is in this register here. All right, so that's really what I'm doing. So I set it to 18 milliseconds, and then I'm setting my initial position, because remember, this is just setting it up, right? The user hasn't pushed the switch yet. So this is just setting up the servo initially, the timer and the servo. So where would you put the camera if you haven't had any switch presses already? Well, it depends on what the thing is. In this case, I'm saying put it in the middle position. You might say put it at the left or the right. That's your choice. But in most applications, robotics especially, if you don't know where the thing's meant to be, it's probably safest to say start it in the middle. Right? Yeah, who knows? Again, this comes down to your experience, your knowledge of the actual applications. I'm just saying that, well, I don't know yet what's going to happen because the user hasn't pushed any switches yet. So I'll set it in the middle position. All right. We're not using interrupts, notice. So this is an example where we don't use interrupts with timers. Nearly always we do. This example, we don't. And we clear all the interrupt flags. The interrupt flags are these 4 and this one. This is not an interrupt flag. These are not used, these bits. Clear all the interrupt flags, because if there's already an interrupt has occurred on those pins, just clear them anyway. It's always good practice to clear the interrupt flags when you set up a device at the end, before the program becomes live. Okay, because even though we're saying don't use them here, we don't want any weird effects. If we subsequently enable interrupts later, then these interrupt flags, these could still have an interrupt pending from before we even configured this time, and that would be really dangerous. And then basically this goes through. This is example 2, and the only difference here is, so it's basically the same program, right? The difference is, here I have, imagine rather than pushing switches, imagine the controller's got a joystick like a game controller, and they can turn the camera. They move the joystick and the camera will also move that way. So this is more like maybe you see in these programs where there's some problem with security. Someone's running around in the street and the security are trying to keep an eye on them or something like this. Some problem is happening, and the security guard's got a lever they can turn, and the camera will go where they point it. And so instead of the switches, now we have an analog input, and we're going to have a variable resistor. So it's just like a game controller, like a joystick. You can point the camera where you want by turning this lever. And so we now don't need the switches anymore. Now we need an analog input. And so this program is exactly the same, except everything is pretty much the same. So it's same as example 1. The only bit you'll find is different is the A to D converter, which I'm not going to go into great detail there, because again, we've done that in a separate lecture. But the point is, we're going to choose which channel we want. In this case, it's going to be channel 2. We're going to connect a variable resistor to that input pin, and we're going to read that value. And based on that value, we're going to do some maths to convert that value into a position value. And we're going to allow the camera. Now, the camera won't move necessarily completely smoothly because of the way we do the conversion maths. It may move in small stages rather than completely pure sweeping. It depends on how fine the maths is in terms of the small increments, and also how fast the person moves the controller as well. So they would need proper training to use this, because if you've got a security camera that's doing this, it's useless to anyone. So you need some, and you could do the stabilization in the code, or you could do the stabilization by training the operator to move it slowly. Okay, both are useful, I would say. Okay, so this is all just turning off the digital inputs. We talked about all this before. Same stuff as before. Starting conversion. All this is the same as before. The only tricky bit is that the value from the A to D converter, I'm using just an 8-bit value. So I'm getting values between 0 and 255, and I've got to convert that into a value between 750 and 2250, because that's the range of my servo movement. That's the range of my analog input. So I do this formula, which I'm not going to explain to you because you can read later. It's just a simple bit of maths. It basically says, take a number in that range and translate it to a number in that range. Okay. And obviously the minimum of this value is always going to be 750 plus something, because 0 there must relate to 750. So that's what that's on the end for. And this is just really dividing the range. Yeah. And this value here will end up, whatever this is, will translate onto whatever between those two values there. Okay. That's a simple bit of maths. You can work that out for yourselves. And then we put the output of that value to the LEDs as well as a diagnostic. Now think about this. This is going to be a complicated program to test, right? So why not use the light so you can see that the analog part is working? Even if the servo doesn't move, you will at least know where the problem is. Is the analog part working correctly or not? Because I've got the LEDs which will tell me, hey, the analog's working, but the servo's not. Or maybe the servo's not working and the analog's not working either. So maybe the problem is in here. So always have these diagnostics in your code, in your coursework, equally important as it is in something more complicated, maybe like this. Having direct feedback, visual feedback is very valuable, rather than having to do all kinds of external testing and run test code, etc. This is an instant feedback as to what's happening, certainly. And if you were making a product, then you would take this line of code out at the very last moment when you've done all your testing. You would just comment this line out before you send the final version, because the camera operator in the control room doesn't really need to see all these LEDs flashing, right? But when you're testing it, you do need that. So you could this will be part of your code, and you just comment this in the final version. And then if you need to update the code in the future, you can uncomment this and get diagnostics again in your test model. Okay. This is a simple robotic arm that I built to demonstrate this with two servers. I haven't set up a demo for it, but I think the arm, just to prove this really does exist, and where you can see the picture of it, the arm is actually here, covered in dust in my study. There is the dusty robot arm that is in the picture. I'll put that back in a minute. Right. So this is a robot arm I made some years ago, and I set myself a goal to build a robot arm in 1 hour, from nothing to 1 hour. And I did. It was pretty rough and I had to tidy it up later, but it worked. And this is the robot arm. It took me an hour to build. And that was this is old Meccano that I used when I was a child. I've still got it. And you can make anything out of this stuff. It's brilliant. And you can make a little base, and there's a servo there, an arm, another servo here. And by controlling the two servos, you can use things like that. A nice trick is to pick up a set of car keys off the table with it. Okay, you have to position it. It's like those games at the fair where you have the clip, you have to come down and grab it and try and pick something up. But you have two servos to control. Okay, simple application, but it shows a lot. You can do a lot of learning with a 2-servo robot. There's a lot of control needed to even to pick up a set of car keys with this. Takes a bit of skill, and you have to, obviously, if the program's not controlling the servos precisely enough or smoothly enough, it won't work. So you can imagine a simple thing like this can give a very large amount of learning opportunity. And we made these, the students then made these at the university, and hopefully they learned a lot from doing it. You can see I've just literally bolted the servos onto some old Meccano, and in the pictures of the servos you've got, there's got round discs on the end. These are just slightly different. These were slightly different ones. You can get all kinds of different. These are called the servo horn, goes on the top, and you get different shaped ones. And these were just much better for bolting Meccano onto than the round ones. That was all that was different there, because I made bigger holes. These have small holes. I just drilled the holes, made them bigger, and fit Meccano. Straightforward idea. All right, and zooming in, you can see literally it's a servo bolted onto the framework with these holes, and this is your arm, and these are the wires. This is wires going to the other servo, and so you could make in your flat, probably with a bit of wood, you don't have to have Meccano, a few bits of wood and some servos, you could make a little robot arm for playing with. It's that simple. And once you start doing this stuff, you can get a bit too interested in it, and it takes over your whole life, and you suddenly become a robot expert. But it's a lot of fun, and there's a lot of jobs in robotics, so bear that in mind. All right. And toys, a lot of toys have robotic movement within them. So there's a whole load of medical equipment and so much more, all based on these simple servos. Anyway, these are just different pictures of it, so you can see how you would build a really simple servo robot. And that's the end of that set of slides, I think. Obviously, here I've got a little extra board that takes these signals and patches them on, because the microcontroller I used had both the wiring on the port. It was all based on these 10-bit connectors, so I couldn't plug these straight on. What you would probably do is take your servo connector and plug 3 jumper wires into the end and connect them directly on the servo port. It is probably the easiest way, or onto your breadboards probably, and then onto the servo port is probably a safer way to do it. Okay, so that's the first of the 4 lectures. The second one is very brief, so I'll do the second one and then we'll have a break, and then we'll do the other 2 mini lectures. That's 1 mini lecture done. Are there any questions on that one before I do the other mini one?
Yeah, there's a question from a student. Could you come forward?
I have 2 questions. One is this ADC and the timers, which one is prioritized first? Prioritizing.
Right, hang on a second. Let me go back to the code, and then you can ask the question again, because I didn't quite get the whole question. So you said something about the timers and the A to D converter.
Yes, which
what
one?
What is the actual question?
There's prioritizing in the interrupt, right? There's hardware interrupt, timer interrupt, and ADC interrupt. Where is the ADC? I didn't find it in the sequence.
Oh, you mean in the actual manual?
Well, I don't know where it is. I just asked. I didn't find it in the sequence. So.
So do you mean in this code?
Not in this code.
No, so in the manual.
In the manual.
Oh, okay, in the manual.
Yeah.
Yeah. Right. Hang on. So here is. Hang on. I've got to find the diagram, the right. Right. So.
We can see. Yeah. Now we can see you.
Now, if we go to 100% first of all.
Yeah.
On this, right, and then we what I've done is I've closed the index. I think that's okay. Let me just close and open that again. All right, it won't take a second. So just make sure you open it as a PDF, because you do need, let me move this across now. You do need the index. You cannot do this without the index. It just takes too long. So you see the index down the side here, right? So go to section 14, interrupts, and interrupt vectors. Okay. Yeah. Is this where you looked?
Yes.
Okay.
ADC.
Right, hang on a second. I will now get rid of that, make it slightly bigger, and I can get rid of this now because we're in the right place. So, in fact, I could have just pushed there. I don't know why I didn't do that on there. It doesn't matter. Now, so we have the hardware interrupts, the PC interrupts, the watchdog timer, the timer 2, timer 1, timer 0 should be next. Then we have the serial peripheral interface, which is the serial we talked about a couple of weeks ago, and the USARTs.
Right.
And then we have the analog comparator, and then we have the A to D converter.
Okay, thank you.
Okay.
Yeah. It's clear now.
What was the other question? You said you had two questions.
Yes, the other one is you have server 1 and server 2. And do you use the server 1, server 2 to separate the functions to choose the one of them? Or
Yep.
you recommend to use this interrupt or timer to separate which one to choose? Is it depends on the function or any recommendations on that?
You're talking about how I'm controlling two servos with one timer?
Yes, in your prototypes.
Yes, right. Okay. That is a very good question. I'm surprised everyone didn't have that question actually, because I probably should have mentioned a bit clearer. Let me show you that in this particular code, right. So in this particular code, I'm only showing output compare register 3A, right?
Yes.
And I'm not showing the others because this particular code is only for a single servo. It doesn't control my two servo robot, right? What you would do, you would set output compare register 3A to one value and output compare register 3B to another value, right? And
No,
that would then
sorry,
have two servo outputs. And if I show you on this, the actual, oops, sorry, that's not the one I meant. I don't think I've actually on the sample code. I'm not sure I do find it eventually. Just give me a chance to find the actual. It might only be in the 1281 sample code. So you see PWM servo double potentiometers. Can you see this?
Okay.
Yeah.
Yes.
That, I don't know if you can read, it's very small writing there, but there is one in there, and that will show you how I do it with two PWM signals with one timer. If you look at that code.
Okay.
All right. But basically, if I show you the difference by coming back to this slideshow again, right, and we go back to where that timer setting is, basically what you would have is separate values for 3A and 3B, right? And if we go back to the diagram of the wave generation, right back to here, right? Now, what you would have is two waves coming from the same timer. They would both have the same end point. So they both have the same, this bit is the same for both, right? And this bit is the same for both. But instead of having just one of these, you have two different ones of these. And one of them controls one pulse and the other one would control the other pulse.
But is this in one server or in both servers?
Each servo would have its own pulse.
Okay. Okay.
But only one timer is needed.
Okay, that's clear.
Because you'd have two of these waves, right? Two of these waves would be produced and they'd be on two different pins.
Yeah.
But the same timer is producing, so the start point, this point here is the same for both, but the point where they change, you'd have two of these instead of one. So output compare A might be here, output compare B might be here. And that would cause the other pulse to change slightly differently. This diagram only shows one.
Right.
All right. Have a look at that code where it says double potentiometers code. Okay, that code I showed you in the archive, right?
A lot.
Yeah.
It help a lot. Yes.
Okay.
Yes.
Have that. Look at that code and look at the way the timer is configured in that code, and you will see that I'm using output compare register A and B, or maybe it's A and C, or B and C, because there's three altogether. I can use any two of those three.
Okay.
All right.
Yeah.
So it's a very good question. Everyone in the class should have had that same question, really, because I should have explained that and I forgot to explain that point. All right. It's quite important. If you want to use all three of those output pins, you have to basically, you'll get 3 of these signals from one time and not one. You'll have 3 of these midpoints, but only one endpoint. All right. Any other questions?
No.
Okay, so I'll now very quickly cover the second mini lecture, which is, you'll be grateful to know it is very quick, but it doesn't mean it's not important. So, in fact, what I'll do, I'll cover the quickest of the 4, not the second one, because that's actually another slightly longer. The quickest of the 4 is number D. So I've done A, I'll do D, and after the break we'll do B and C. So pull-up resistors. This is a quick set of slides, only about 5 slides. This is really important, and I know most of you have already done some of this because we've mentioned it in a few lectures. We mentioned it several times throughout the course, and right at the very beginning with the LEDs, you had to do this to get the LEDs to work. But I want to give you the theory behind it, so at least at the end of this course, you don't just know my examples, you actually know the theory that you can use if you need to do your own calculations and so on. So the basics, and they will be basic, you can read the slides in detail later, but the slides are here and everything you need to know is here. So very, very important is a thing called Ohm's law. V equals I times R. Voltage equals current, I is for current, times resistance. And so we can rearrange this formula. You can rearrange any formula with 3 parts. So if it's V equals I times R, we can also say it's I equals V. If we divide both sides by R, we can say so I times R divided by R is just I. V divided by R is V over R. So we can rearrange this formula to this formula. And this is very important because if we want to calculate the current, we need to know the voltage and the resistance. We can also calculate resistance by divide both sides by I. We could have R equals V over I. So we've got 3 different formulas, and we can calculate any part we want from the other 2. Now, normally the thing you want to know is the current. You want to actually predict the current because the current, you need to know how much current will flow through your LED, for example. So if we have 5 volts and 1000 ohms, we will get 5 milliamps. Okay, simple calculation. And we have an LED, maybe it says in the manual for that LED, it must be typically a low power LED will be between 3 and 20 milliamps. So 5 is good. And if we wanted it to make it brighter, we could change the resistor, put half as much resistance. 5 divided by, say, 500, if we had approximately 500, then would give us 10 milliamps. So the LED would be quite a bit brighter, okay? Now, pull-up resistors are also important, and we did cover this during the course, but I want to make sure this is completely crystal clear as well. If we have a switch and you don't have a pull-up resistor, you just have a switch and a ground, like this, or the switch and the 5 volts, just connecting like that. This is a bad circuit because when the switch is connected, you have ground on that pin, which is fine. But when the switch is open, you do not have anything on this pin. You can't suggest that because the switch is not on ground, it must be on high. It's not. It's basically when the switch is open, this is on nothing. This is it could be just a random value on that pin. We can't be sure what the value on that pin is. We can't be sure it's a 1 or a 0. It's a very dangerous thing to do. If this was in a safety critical application, you will lose your job, and someone worse than that, an airplane could crash, right, or something like this. It's a very, very bad. So we don't want that. So what about this? Okay, well, this is also bad because although it's an improvement on that in some situations, i.e. if we close this switch, we get a 0. If we close this switch, we get a 1. So we have a slight improvement. We also introduce a new danger, right? If we have them both open, we have the same problem. That's not a new danger, that's the same danger, but here's a new danger. If we connect both of them together, we short circuit the power supply and the microcontroller will reset itself. So we've got even more danger now. We're randomly resetting the microcontroller, because when you release them again, it will reboot the microcontroller. But even then, while we've got them shut, we'll drain the power supply as well. And we could cause even heating in the circuit. So this is incredibly bad. This is bad. This is incredibly bad. So you can't do those things, right? Now, what about this? A switch that's got 2 positions. This is much better. And this has some uses. This could be used, right? Because the switch is either that position or that, and it can never connect this to this. But there is still a moment when the switch is in the middle. It goes from here to here. There's a moment where it's not on any. And the microcontroller works very quickly, remember. So in terms of the microcontroller, there's a gap there where the microcontroller is sensing some kind of who knows what in the middle. So that's dangerous, but better than these two. But you need a more expensive switch to do it. And these switches are physically larger as well, because they're internally, so they cost more and so on as well, and they're heavier and everything. So if you're making nice little devices and that, these switches are just generally not so desirable. So what if we do this, right? What if we have a switch and a resistor, and when the switch is closed, because this is much more current can flow through here, this will overpower this small amount of current flowing through here. This will be overpowered, more current can flow here. So this will be 0 volts when we shut the switch. But when we open the switch, this will now, enough current is flowing through here to make this 5 volts, because this only needs a tiny amount of current to make this go to 5 volts. And this will be much more current than is needed. But because when this is shut, because we have this resistor, we are not damaging the supply, and we are not, so we're not draining the supply so quickly. We are still actually draining the supply, but not so quickly, and not enough that the voltage will drop and this will reboot. So it's much better in all respects. But you see, this needs extra components, it's extra wiring, it's extra cost. It's not desirable to keep putting extra bits. So what if we have a pull-up resistor built into the microcontroller, which we do have? Why don't we just turn that on? So then we only need our external, we only need our switch, but internal we have the resistor. We can turn this on and off with software. So this is what, when we say to put the pull-up resistors on, they're already in. All we've got to do is turn them on in that programming, which I've shown you in a previous slide somewhere earlier on, but I think it's also potentially on the next slide. We just turn the pull-up resistor on, and then we have our resistor, but we don't have a physical external resistor. And then we can use these miniature cheap switches with less components, less wiring, less size of the circuit, everything simpler. But we still have the pull-up resistor, all right? And that's, yeah, it's here, how to set it on. An example of setting them is here. I'm not going to, as I say, I'm not going to dwell on this. You can look at the slide later. This explains how to set, there's 2 examples here. Set all of port B, but just set the pull-up resistor on 1 bit, or set all of port C and set all of the pull-up resistors. Obviously, it only works when the port is set for input, right? So just go back, kind of obvious, I would hope. But when this is an output bit, you don't want the pull-up resistor on. In fact, that would be bad, right? Because you're messing up the signal somewhat. And if you put the pull-up resistor on accidentally when you're doing something like analog input, something like that, your analog signal will be screwed up by the pull-up resistor. It would basically change the value of the value, and you know, things won't work properly. So again, another thing to be aware of, if you're using analog and you find the voltage coming in is not what you expect, that's another thing to be careful of. Have you accidentally set the pull-up resistor? Worth checking, definitely worth checking that, because that would be an example of why your analog system won't work when it should do. So these are things to be aware of. Okay, any questions on that? And then we can actually have our break. Oh, sorry, there is a few more slides here, just very quick. Current limiting, so this is the current limiting resistor in use. Okay, so we saw the at the beginning, this concept here, right at the very beginning of the, you know, working out the current flow with V equals IR, the Ohm's law. And then in actual use, so you can do it either way. So you could have your output pin, current limiting resistor, and then going through to ground, or going through to 5 volts. So you don't have both, you have one or the other, and the flow of current is, so for B, the current flow is here, and for A, the current flow is here. These are two alternate diagrams drawn together. You don't have load here and here. You have load either here or here, but this is just showing you both variations, A or B, not both, right? But let's assume B position. Then when you turn on your port pin, your current is flowing through the resistor and through this device here, like this. This is the usage. And basically, by calculating the current, you are doing several things. You're saving power, you're preventing damage to this device, and you're preventing damage to the output pin. Because if you look in the manual under electrical characteristics, so if you search in the menu of the manual, look up electrical characteristics, it will tell you the maximum current that you can put out of that pin. And therefore, you should make sure you don't try to output too much. But also, when you're having inputs coming in, there's a limit to how much current can come into the microcontroller. And some circuits, you may want to isolate the device that's sending the signal, especially if you're connecting the microcontroller to high voltage things. So for example, you could have a 12-volt sensor circuit connected to your microcontroller, which works at 3 volts or 5 volts. You can do that as long as you have the right resistors in place. All right, so you might have a circuit with a sensor that works at 12 volts, like some PIR sensors work at 12 volts, and you want to connect it to a 3-volt microcontroller. Well, don't do that until you know for sure you've calculated that what current will flow through here, because that's really the important thing. And you can do those things, but if you're a novice with your interfacing, then don't do it, right? Make sure you learn the interfacing first before you do things like that, because you can, as I say, you can even, and again, definitely don't do this until you're an expert. You can have voltages, you can have a mains connected sensor with 250 volts here and a diode to rectify that and a resistor. This is definitely not for beginners, but you can do that. And you can actually, as long as the voltage, essentially the effective voltage here, and that in terms of that, I mean the current really is limited by using the correct value resistor, and of course in that case a diode and a capacitor. There'd be more of circuitry, but you can basically put other systems and connect them into this, but only if you know what you're doing. But that's why knowing what you're doing is important as engineers. That's why it goes around in a circle now. That's why you need to know the formula, and you need to understand electrical characteristics carefully, and then it opens up your scope to what you can and can't do, what is safe, what is not safe, etc. Okay, and so here's an example then, taking that previous diagram with an actual example. If you have the 1K resistor we talked about before and your LED, which works in that range of currents, then if you have a 1K resistor and a 5-volt power supply, then you have 5 milliamps flowing through this circuit, and that will be on, not very bright, perfectly good for like an indicator LED, not bright enough like for lighting or anything like that. This is definitely just an indicator type LED. All right, and these are formulas. And if you say, well, what if I change that to a 470 ohm, what would it do? Well, you could, a lot of people would just try it and see what the brightness looks like, but the proper way to do it, of course, as engineers, is to calculate it, check that that value is in the range, check that that value is in the range for here as well, for this port, and then connect it. All right, so you know, if you're a hacker, you would just try different resistors till the LED looks good, right? If you're an engineer, you will calculate it and then just plug in the right value. All right, any questions on that?
No, I just want to add that the Atmel has internal pull up and pull down resistors, so you can choose.
Does it?
I think so.
You sure?
I think we can. I saw it in my ADA code. So
really?
Yeah. Well, we can check the manual.
Yeah, I don't think it has, but okay. we can check that. I don't think it has, to be honest.
Okay. That could be my error then. I'll double check that.
Yeah. Okay. Right. Let's have a 20-minute break.
Yep.
So 11:59 exactly.
Yeah.
See you soon.
Yeah.